First, I'd like to start to thank the organizers for inviting me to this extremely well-organized event. I appreciate it. Very good. So, title of my presentation is Hydrodynamic Simulations of Rotating Black Holes and the Aronoff-Bohm Effect. And perhaps I should start to explain a little bit the background behind my line of research. Also, probably most of you have not heard about that before, so I'm working on what's called analog gravity. And in order to explain what analog gravity is about, I have to talk a little bit about quantum gravity and how these kind of studies fit within the bigger picture. So, of course, we have these extremely beautiful two theories defining modern physics. So on the one hand, we have quantum field theory, and on the other hand, we have general relativity. And so both within their own respects are extremely well-tested and amazing theories. But of course, the hope is somehow that, or we believe there are regions, there are situations where you have to combine these two theories to a more fundamental theory dubbed as quantum gravity. Now, of course, there is a more modest way of combining these two theories, and already Balog talked about this earlier on today, and that is simply by saying, okay, I take some aspects of general relativity, namely the gravitational field is this space-time geometry, and you don't worry so much about the dynamics behind that. You just take the space-time geometry as a given entity, and you can see how my fields, which I can quantize, classical or quantum fields, how they propagate on this space-time geometry. And if you then, as Balog pointed out this morning, neglect back reaction effects, so if you can also assume that, for example, you have some back reaction effects of the quantum fields onto the space-time geometry, then you have what's called semi-classical quantum gravity, or semi-classical gravity, excuse me. But if you forget about that and you just say the gravitational field is classical, I don't care how it changes, or let's say the effects of the fields, the matter fields propagating on that are very small, then what you're in is this region which is called this field, quantum field theory, or classical and quantum field theory in curved spacetimes. Now, this is perhaps a very conservative way of combining these two theories, and it's not as prominent as finding a quantum gravity theory. But at that level here, there are a lot of strange and really amazing effects going on. For example, quantum field theory in curved spacetimes predicts, for example, how the particles in our universe are being created. It tells us what the fate of black holes is, how they can evaporate away their mass, and how they can lose their angular momentum. So this is really where, at the moment, I would say, is all the action is. And my line of research is simply to find systems that share some properties with classical and quantum field theory in curved spacetime in everyday systems. And in particular, I'm interested in fluids, ordinary fluid flows, and how small perturbations experience this fluid flow. And if the physics I'm considering in both systems is the essential one and they are equivalent, then I can mimic all these fantastic effects predicted from classical and quantum field theory in these analog gravity systems. So, also because this is an interdisciplinary conference, so I was thinking of how could one explain that to someone who has never heard about special or general relativity, quantum field theory in curved spacetime. Now, everybody knows, of course, the wave equation and from quantum mechanics. And when you, of course, want to, or classical mechanics, if you want to then rewrite that in a more fancy way, you can say I can rewrite this equation on flat spacetime geometry, which is also called a Minkowski spacetime, by rewriting it in this way. Now, if I now want to consider how these fields propagate on a general curved spacetime geometry, then what you can do an ad hoc substitution by simply replacing your flat spacetime geometry with a general curved spacetime geometry. And here, of course, you can consider various different effects, such as black holes, rotating black holes, or just, for example, our universe as a whole, a Friedmann-Robertson-Walker spacetime geometry. Now, obviously, what you can also do, you can then either say, looking at classical fields, this is a classical massless scalar field minimally coupled to the space-time geometry. And then you can say, well, I can either look at classical effects or I can simply quantize these fields. Now, what you need to do is, of course, to say, what I'm interested in a regime where I'm saying, well, if I also consider that this space-time geometry is obeying Einstein's gravity as a dynamical equations for this metric rank 2 tensor here, describing the gravitational field, then of course I'm assuming that whatever happens to my matter fields will not backreact in terms of the Einstein equation. So I'm neglecting the backreaction effects. So now, can I have another system where I find the same set of equations? And I think 20 or 30 years ago, Bill Unruh was giving a lecture on fluid dynamics, and he thought about the appearance of horizons or causally disconnected areas in fluid flows. And so the way he thought about that was in the following. Suppose I have a river flow, and at that end here, I say that river flow is almost zero, while when I'm going to the right, it speeds up. Now, let's be a theorist, and let's assume I can speed up this flow without any difficulties beyond supersonic velocities. Now, you can be here, and you can say, well, I look at small fluctuations. If I linearize my fluid dynamics equations, namely the continuity equation, the Euler equation, and of course there's also an equation of state, but I'm assuming a barotropic equation of state for my fluid, so a very simple one. And making several assumptions, it's inviscid, irrotational, incompressible. And so this is the setup here. And I'm looking at the sound waves, and if the flow is addressed, they can propagate equally fast in all directions. Now, if I'm giving I'm in a region where, let's say, the flow has a non-zero velocity going to the right, and what I'm seeing that sound waves propagate faster with the flow than rather propagating against it. Now, then you can imagine if I have this region where the flow becomes supersonic, then in this area here, I can define an analog or an effective, in a sense, event horizon, if you wish, or apparent horizon, where I'm saying signals sent from this side can only propagate with the flow, which is a supersonic flow region, while on the other side here, signals can propagate in both ways. So I can, from outside here, from this region here, I can signals to the right, but once I'm beyond this area here, I cannot send signals outside anymore. And so then Bill went back and did the calculations in his office, and what he found is when I linearize this set of equations, I can rewrite it. It's not a trick, it's just a way of rephrasing the equation for the perturbation, the little perturbations in the fluid flow, in a way such that you get this wave equation, which was on my previous slide, where now here I have also a GIB, but obviously this is not the real gravitational field. What that is an effective or acoustic or emergent metric. And this metric here, what enters here are simply the speed, the velocity, the propagation speed of the little ripples in your system, and the background flow of the fluid flow. So, and you can see already, so this horizon here as defined as in our little Gedanken experiment is simply when the two, this G naught naught here becomes zero when the propagation speed of the little ripples is equal to the background flow. So that sounds like a neat way of understanding this, or having an analogy which you can explain to your children or to anyone. You can explain in this simple setup how one could understand black holes, for example. However, this is not just a theoretical tool. These things really appear. So in particular, all of you have looked at Whitehall Horizon when you go for a hike and you look at river flows, and there are stones in the river and the water flows over and it's very shallow. Then what you get automatically are this effective black and Whitehall horizon. And the reason is because in a setup like this, so this is an open channel flow from our previous experiment taken in Vancouver at UBC, and what you see, we emerged an obstacle into a shallow, in an open channel flow, so water is flowing to the right, And then if the water gets shallower, the propagation speed here of the surface waves gets smaller. It's proportional to the height of the flow, while of course due of continuity of mass, if the water gets shallower and you have a constant flow rate, the water has to speed up. So what you get here is an effective black hole horizon, effective white hole horizon. So a white hole horizon is just a time reversal of a black hole horizon. So in a black hole horizon, everything can enter, but from inside, nothing can leave this region. Black hole horizon is the opposite. You can leave through a black hole horizon, this is what we call here this critical region, but nothing can enter from outside. So naturally, in some systems, you get this set of effective black and white hole horizon. Now, perhaps the most remarkable issue raised in Bill's original paper in 1981 was, which the title already indicates, that he asks a question. He says, experimental black hole evaporation. So at first, it seems, of course, a crazy idea in this completely classical system. How could you learn something about this, what perhaps most of you think is truly quantum effect? So, but what he proposed back then is, I say, can we use these analog gravity systems to actually mimic classical and quantum field theory in curved spacetime, meaning looking what's happening actually to these fields propagating. Do they see the same strange effects, such as Hawking radiation, the effect which is associated to the loss of angular momentum, that's superradiance, or, for example, how particles are being created in our universe? And the answer is yes, that can be done, and it has been done, and remarkable progress has been made over the last, I would say, 10 years, where people have managed to recover Hawking radiations or parts of Hawking radiation in fluids, superfluids, especially Bose-Einstein condensates, and optical systems. So this is, and there are really beautiful new papers out every year now, and there's a big debate going on in what sense these fluctuations are actually, how this process, are they really seeded from the quantum noise in the system if you use a superfluid, and how can you prove it? So what I want to talk about now is something I'm really excited about, and these are my new experiments, and that's about, now I'm looking at something a bit more challenging. I'm looking at rotating black holes, and I want to see how rotating black holes can slow down and lose their angular momentum. And there is another group in the UK, Daniele Faccio, he's also looking at these things in superfluids, in fluid of lights, actually. So the effect I'm after, I want to understand how rotating black holes lose their angular momentum and how robust and universal these effects are. So rotating black holes are very complicated objects. They have several difficult horizons. They have strange singularities. They have ring singularities, many, many things. And the first question when I was a student, I asked together with my former PhD supervisor, Matt Visser, was, can you really find an analog gravity system that mimics the outer parts of the Kerr solution? How much can you mimic? So the first thing, there was a paper not long ago that showed that you cannot map the Kerr solution onto a spacetime solution which is conformally flat on the spatial slide. Now that sounds a bit heavy, but one can explain that. What you can see here in this metric, here this identity matrix here, it's a 3x3 matrix where on the diagonals are the ones, which means all of these analog gravity spacetimes are spatially flat. Conformally flat on the spatial slice. So this already showed back then that you cannot mimic all of Kerr. Now, but what you can do is actually you can mimic the equatorial slice in a Kerr black hole in a magneto-hydrodynamic fluid flow. And at the equatorial slice, that's where most of the physics actually is, or all of the interesting effects, the effect that tells us how the angular momentum is lost, is occurring. So you have to have a complicated fluid flow, but you can also ask yourself, well, what if I want to make a very simple experimental setup and I cannot use magneto-hydrodynamic flows? What about common bust-up vortex flows? That's actually the picture of my experimental setup. And so it's very easy to understand what's happening and what's so special about rotating black holes by looking at fluid flows, stationary draining fluid flows. with non-zero angular momentum. So you have the total velocity. Let's assume a two-dimensional velocity field. I have a radial velocity and I have an angular velocity. Now, I can define a horizon which is called this ergosphere, in this sense, or this effective ergosphere, when the total velocity is equal to the propagation speed. So meaning when a perturbation, a small perturbation here on the surface would enter this region, it gets dragged with the fluid flow, and what's called also, it's referred to in general relativity or in gravity, it's called frame dragging. Now, the event horizon is defined when the radial component of the velocity field is equal to the perturbation speed of the little ripples on the surface. So these are the two horizons. And again, this is not completely like a Kerr black hole, not even the equatorial slice, because there are some very interesting effects going on associated to the fall of the angular momentum. And this is where the effective or water equivalent Aronoff-Bohm effect comes in, which will I explain later. So these are not quite really the black holes we have in mind as to physical black holes, but they have all the features to actually look for this superradiance scattering in these systems. So what is superradiance scattering? So there is superradiance scattering. It means that if I have a wave with a certain azimuthal number, for example, scattering with a rotating black hole or with a bathtub vortex flow, so let's say I normalize what's going in the amplitude of this wave by 1, and what I see is if it scatters with this rotating black hole, it comes out with a reflection coefficient which is larger than 1. And this can be explained. So here I have the equation for the superradiant for the scattering. Here, scattering amplitude. When I look at this is the omega of the wave. So I'm sending in a wave with a certain frequency. This capital omega here is the angular momentum of the rotating black hole at the event horizon. And you can also consider black holes with a charge, so Kerr-Newman black holes. And what you can see is if, of course, omega is small enough, and this m here is the azimuthal number of my wave. I have a wave with an azimuthal number and a fixed frequency. And then I can see if this omega is small enough, then this changes sign, and the wave that comes back has basically increased its amplitude, if you wish, in a simplified way. So to explain this in a more sophisticated way, you can say, well, I have this second-order hyperbolic wave equation. I can associate a conserved current with that. And this conserved current becomes quite simple. It's the amplitude of the wave, Kolmog's frequency, and the group velocity of the wave. And then you can imagine, so if I have a black hole and I just say what about thinking of it as in form of a potential, and I say, so I have a hyperbolic second-order wave equation. So outside the black hole here, I have right and left moves, ingoing, outgoing solutions, and on the other side, inside, in principle, I could also assume two solutions. Now then I can say, well, everything that goes into this rotating black hole has to come out again. And then you can say, well, I send one in. Here, this solution, because it's an event horizon, means that nothing can escape from this rotating black hole. So here is nothing coming in. And then I can see what's going back out and what's going into inside the black hole. And if you put that together, you simply get this amplification process. And that is because this particle current that goes into the black hole is negative. So effectively, you can think of this process because you're sending into negative particle current goes inside, you're extracting, in this case, angular momentum from the black hole. So it's just a simple scattering process, and the question is, can we see this in these analogs? So we also looked at all of these analog gravity systems are also quite interesting from a different perspective, because they are all of these media are dispersive, which means that if you want to compare it to some sort of, or related to quantum gravity studies, you would give up Lorentz invariance as a fundamental symmetry. And in this sense here, if you like to say it this way, you could say, well, in these analog gravity systems, you have an emergent symmetry with respect to the propagation speed of these little ripples. But when you go to shorter distances, shorter wavelengths in this system, what you will see is that this medium, for example, water, has a substructure in a sense. And so this effect goes away, this symmetry. And of course, if you want to go to, at the end of the day, I'm not saying that in water this is given, but in Bose-Einstein condensates, it's perhaps a little bit better defined. So what you see is that if you go to higher and higher energies, at the end you should be left with a molecule. So in some sense, it has to have some dispersive effects in the sense that this emergent symmetry is not a fundamental symmetry. So, but you can also look at the superradiance if you have this dispersive media, and then of course you get a more complicated scattering process. You have, at the same frequency, you can have various different excitations in the system. And so, but still you can define an overall amplification process, or you can look at the superradiance scattering and see if it's still there, but you might have to look for some of the scattered waves in a different wavelength. So one of the other things we did is, I think most of you have heard perhaps of superradiance in a different context from a Seldovich cylinder. And so one question is, so how does superradiance, for example, from the Seldovich cylinder also compares with superradiance from black hole? So this can actually put together if you're assuming, when you look at your potential, before I said, this rotating black hole is just a gravitational potential with this special boundary condition at the event horizon where nothing can go out. But you can think of a more general, can I write down a general potential which includes both effects, superradiance, and for example, this Seldovich type amplification process. So Seldovich cylinder is this scattering of electromagnetic waves by a rotating cylinder made of electric conductive material. And what you need to do is, if you want to write down a more general potential, you also assume a complex imaginary part of the potential. And what you can see then, you can derive again the scattering amplitude, and what you see is that for black holes, it's associated to the real part of this potential. And if you have the Seldovich type cylinder, you don't have that contribution, but you have that from the complex potential because you have dissipation in this cylinder. Now, so in the one case, it is due to boundary condition because you have less coming out of this black hole in fact, if you have a strict event horizon, apparent horizon, then there's no outgoing solution from the inside of the black hole, but you can also relax this condition. So it's an effect solely on this, that you have this special boundary condition, which in the black hole is given by this event horizon. Now in the Seldovich cylinder, it's a dissipation of the system, so you create negative particle currents, and you need a mechanism to extract them from the system. This can either be done through dissipation or through these special boundary conditions. So we're also trying to set up an experiment to test this, but the experiment I want to talk about is to actually set up an analog rotational black hole and test how universal, how robust this superradiance scattering is in these analogs. So this is a picture taken from our analog black hole. Looks pretty cool when you compare it with an artist's depiction of a rotating black hole. So that's of course accidental, but so this is our bathtub vortex flow. And so the first thing you need to do is you say, so I have an experimental setup, and I'm assuming that, of course, I have this superradiance scattering. How big is it? Because when you do an experiment, it is very important how big the effect is, if it's actually detectable. So we did some modeling in some parameter space search recently. So we looked at the angular velocity field and the radial velocity field, and then you also have a water height at infinity. So these are, in some sense, your parameters. So the angular velocity field is irrotational. The radial velocity field, we also assume an irrotational velocity field. Obviously, that's only true outside the vortex core, but within this description, this is actually a pretty good approximation. So what we did is we used the fluid dynamics equations within our approximations, and what we would do, we would solve for the water profiles. And then what you can then do, you can numerically calculate where the location of the horizon is. And you can then go through a parameter space search and try to understand what do I need to do, how do I need to set up my experiment so that this effect becomes maximal. So the first thing we realized within this approximation, this what seemingly were three free parameters, this P here associated to the angular momentum and the A to the radial momentum, and the water height at infinity collapses to only two free parameters. That's already made it easier in terms of this parameter space search. And one of the, in some sense, most surprising thing was by carrying out this analysis, so you would calculate the profile, and then you would look at how big is the angular momentum at the effective black hole horizon, which is the most important parameter for this amplification process. What we found is actually that naively one would think that, oh, because the angular momentum has a free parameter b associated, so in principle I could make this as large as possible because I just look at this quantity here. And I say, well, wherever the location of the horizon is, I put this in, but I can make b arbitrarily large, so one would think naively the angular momentum at the horizon could be arbitrarily large. Now, it turns out that if you take fluid dynamics into account, that is not the case. And what you see there is a maximal angular momentum you can get at the effective black hole horizon in these flows, which is given by the Bernoulli equation. And it says it is exactly the potential energy stored at infinity, which you can convert to rotational energy, but not more. So in some sense, there's an equivalent quantity as there is in astrophysics, where one says that this quantity, which is called A over M, A is the angular momentum, and M is the mass of the black hole, and that thing goes to 1. And in some sense here we have the same quantity, because what we realize, it doesn't matter so much what you can map various solutions onto each other by simply dividing by the potential energy stored in this flow. So you also have a maximum angular momentum, and I can just read this off more or less by looking at the height of the flow. So what you can do now is, if you want to go from fluid dynamics to this effective space-time geometry picture. So what you want to do, you want to go away from your fluid parameters, and you want to change to parameters which are meaningful in this analog space-time setup. And that is the surface gravity at the effective black hole horizon and the angular momentum. So we did that, and you see here these contour lines for constant surface gravity, the red ones, and the dashed blue lines are the ones for the angular momentum. And so you see here, when you come closer to this region here, this goes only up to 1 now, because that's when it reaches its maximum value. So what we then did a parameter space in all of these points. We looked at how big this amplification is, and what we found, of course, it depends. It's also different than a real black hole. It does depend on the surface gravity, while in astrophysical black holes for massless fields, it will only depend on the angular momentum at the horizon. So these are... Okay, so let me just say, so this is a big effect. It can be measured in experiment. It's not a big effect. It is still a very small effect, but it's about the amplification we're expecting is about 1.1. So this is the experimental setup. There's a video which I quickly show.
Essentially, the nice way to think about our experiment is that it acts like a very large bathtub. So the vortex that forms in the center here is very, very similar to the vortex that forms above the drain in your bathtub. Hence the name for this fluid dynamical phenomenon, bathtub vortex flows. Our experimental setup is 3 meters long, 1.5 meters wide, and 0.5 meter deep. What we do is we pump water out of our reservoir located beneath the tank. The water is pumped in through 2 inlet arms located on opposite ends of the tank. The rate of water that we pump into the tank is at about 6,000 liters an hour.
Okay, so I have 2 minutes perhaps to wrap up. So one of the things is what we recently overcome are 2 of the main challenges. And one of them is because the measurement is the effect is very small. So one of the things you need to do, you need to find a detection method which maps out the free surface over an area of 3 meters by 150 to a precision of more than 0.1 millimeters. So such a thing didn't exist. We developed that with a startup company in Germany. Quite proud of this. And this method is working. And then the other thing is, to overcome one of the other challenges is how do you excite that system, we actually stumbled onto the water equivalent Aharonov-Bohm effect. So this is our invention here. We have a running joint patent application for this. We're also selling this. If you want to buy such a sensor, please contact me. This is how it works. It is this sensor. It has, you project a pattern onto a free surface. You have two cameras, and it works like our eye. By the difference of these two images, you can reconstruct the surface. You're taking 500 frames a second. You average over a few of them, so you can map the free surface effectively very well for 30 frames a second to an extremely high precision. So the new invention here is because water would be transparent, so what we do, we put organic dye in it, so we shine blue light onto it, it gets absorbed by this dye, becomes green, and this is also how you can take out all the reflections in the system with a suitable choice of filters. So this is the best, fastest, and largest sensor that there is currently in the world, and that's in our lab. And so next week we will start looking for these ripples. It works extremely well. This is a computer image, a live reconstruction of the surface. And so last thing is, when you want to excite this system, it's very hard. In theory and paper, you say, I'm taking a wave with a fixed frequency and a fixed azimuthal number. It's very hard to excite them in a theory, in an experimental setup, one wave with a fixed azimuthal number. So instead of doing this, we're looking at plane wave scattering. So we have to look at the superradiance scattering with the plane wave. However, when you want to do this, what is happening is that this analog black hole has a different fall of the angular momentum. And because of that, there's a long-range effect in there. And what you get is what was already discovered by Michael Berry 10 years ago, maybe even longer, that you have a water equivalent Aharonov-Bohm effect. And this is here pictures from his experimental setup. So you have a plane wave propagating in these flows. What you see, if the angular momentum of this of the vortex is high enough, you have extra wave crests emerging from this vortex, water vortex. And recently, what we've done was Antonin Contin, who recently won a Marie Curie fellowship to join my group. He's also here today. We looked at how would this look at superfluids where the vorticity is quantized. And what we found is if you go to BSCs, when you make the plane wave smaller and smaller, you go to what's called the healing length, what you see is that the wave shift from a single quantized vortex is equivalent to the winding number. And what that means is that actually it's a beautiful way of imaging the orientation and the winding number of these vortices in superfluid flows. So that's it. I'm very sorry for running over time. So a lot of theory results, a lot of beautiful pictures, yet no experimental result. We're going to start going back, and on Tuesday we start looking for this Aharonov-Bohm effect, which is an effect on the ingoing wave. And then we want to look deeper and dig a bit deeper and look how the scattered effect of this is. And in the scattered effect, there should be all the physics that occurs and allows rotating black holes to lose their angular momentum. Thank you very much.